Hi everyone, and welcome to today's lesson on MATLAB for Engineers, brought to you by the GAD Academy. My name is Martin and I'll be your moderator for today's lesson as well. Continuing from our discussion of vectors and a broad discussion on arrays, we proceed with matrices and we're going to find out that there are a lot of similarities in terms of the structure of the lesson and the operations we carry out in general, because most of these are array operations. So we'll start by talking about matrices in general, and we'll look at how to create matrices, indexing and slicing, just as we did with vectors, and then conclude with operations. A matrix is a rectangular arrangement of numbers organized into rows and columns. Now, the size of a matrix is described as m by n. Now, if we recall in the vector case, one of these dimensions was just 1, right? Because a vector was either a single column or a single row. Matrices, you usually have more than one of both of these. So both dimensions become very important and are variable. So m is the number of rows and n is the number of columns. So this means that 3 by 2 matrix has 3 rows and 2 columns. 2 by 2 means 2 rows, 2 columns, and so on. Now, the most intuitive way to think about matrices, or rather one easy way to think about what a matrix actually is to think of vectors first. And if you recall that we defined arrays or vectors as a collection of numbers, related numbers, we think of it in that data set. Then a matrix is just a collection of vectors, right, that have related vectors. So an example you can to help you think about this is if you were carrying out some sort of experiment and you went to the lab to measure certain parameters every day. Now, say you were measuring temperature, pressure, and volume. So you go to the lab, you take a temperature reading on your first day, you take a pressure reading, and then you take a volume reading. Now, at the end of that day, you have one vector, right? Let's call it V1 or V for day one. And that vector will have a value in the first position, a value in the second, and a value in the third. Now, if you go on a subsequent day to measure the same things again, you build another vector. To bring in a vector for the second day, say you do it for a third day as well. Now, what you have now is a vector for each day, but you realize that each of those parameters or variables, the temperature, the pressure, the volume, are also vectors on their own. Right? So you have a temperature vector that contains temperatures from each day, one for the pressure and then one for the volume. So if you put all of this together, you have row vectors and column vectors depending on the variable of interest, whether it's the day you are looking at or whether it's the parameters you are looking at. So in that sense, you can think of a matrix as a combination of independent vectors. Right? Independent in the sense that each vector could make sense on its own. However, the full description of that situation, taking into consideration the relationship between every variable in there, is defined by a matrix. Right? So the matrix combines these vectors together in a meaningful way. Now, in engineering, matrices are usually used to represent and manipulate large amounts of data, as well as carry out certain linear manipulations or linear programming manipulations. So, for instance, you have a system of linear equations with 10 unknowns or variables, and that can be written in a matrix, right? So a matrix equation, which facilitates easy computation and then evaluation of your system. So they are very common and useful in engineering. Now, MATLAB, as we said, is written to work with arrays. So a matrix follows naturally. Now let's move straight into building or creating matrices in MATLAB. Now, just as we did for vectors, there is the manual entry method. There are built-in generators. And then you can merge vectors, right? Just as we've stated that the matrix contains multiple vectors. So you can merge vectors into creating matrices, though there are some rules to consider. So let's begin with manual creation of a matrix. Now you create a matrix similar to how you create a vector. Uh, the rows are spaced and columns are created by moving row elements down. So if you space numbers, you're essentially creating a row. And then once you apply a semicolon, you are moving to another row, which allows you to populate column entries. So let's try that practically. Now we are going to use variables at almost every point. So if this is the first entry to my matrix, now this, if it was a vector, we'll just create a row vector. It's a 1 by 3 vector. So this, you can think of it as the first row in your matrix. Now once I bring a semicolon, I have moved down to another row. And so 4, 5, 6. And then I bring another semicolon. And then that moves me down to the subsequent row. 7, 8, 9. And they should create a matrix. So if you look at the entries here, that is what we have here in every row. And so each of these could have been vectors on their own, as well as these, the vertical 1, 4, 7, and so on. So that is the straightforward way to create a matrix. This is a 3 by 3 matrix. We have 3 rows, 1, 2, 3, and then 3 columns, 1, 2, 3. So every matrix needs to have some sort of a complete rectangular shape. By that, it means that the columns should have the same length, and likewise the rows should. So if we try to create this matrix and we omitted a member from any row, and so we end up obtaining an error, and that is because assuming we wrote this down, we have the first and second row, but this will just have 2 members, and this part fails to complete the full rectangular shape. So this will return an error. I'm going to put that back now. So this should give us take us back to our right variable. So really, you just need to ensure that the columns have the same length. Each of them has the same length, and the rows as well. So that's it for manual entry. Let's just leave it at that. Now let's look at built-in generators, as we did earlier. So the same functions work. The zeros. If I just specify 0, 3, for instance, that gives me a 3 by 3 matrix, right? A 3 by 3 square matrix filled with zeros. Now I could specify the other dimensions if I needed it to differ. So I could go 3 by 4, and that should give me 3 rows, 4 columns. So as such, we can also do ones, and we have the same result. So all the built-in generators apply. Similarly, we can do round, go maybe 2 by 3. And the same thing, numbers between random numbers between 0 and 1. Round n. Same case, drawn from a normal distribution with a mean of 0 and a standard deviation of 1. And we can still modify these according to the same rules. So we could go, for instance, if we wanted to change the range, we could go 10 by rand 2 and 3, and that should alter the range from 0 between 0 and 1 to between 0 and 10. If we wanted to shift or change the lower limits, same rules. So say we want it to be 5. We still want the interval to be 10. So this would shift the interval to between 5 and 15. So we get those numbers. Now, if we want it to be between 5 and 10, we know that is 5 plus the difference between the lower limits, the upper limit and lower limits. So that should be 5. And now this should make it between 5 and 10. So we obtain those results. In the case of rand n, we rand n, we could do the same. So in this case, we shift by the mean. So if we want a different mean, add a mean other than 0, we could just add it 5 plus rand n. And then the values are distributed around 5 instead. If we want a different standard deviation, we multiply by that standard deviation. Say we wanted 2. So that's it. For a good understanding of some more intuition about how some of these random generators work, you can visit the lesson on vectors to jog your memory. Now there's also rand I, which generates integers for your matrix. So random integers can do that. And rand I doesn't need this because it allows you to also specify a range. So you could go lower limit, say I want random integers between 5 and 20. Well, then this should be separated by a comma. And then it's a 3 by 4 matrix I want, 3 by 4. So this is the range for my rand I function. Should be rand I. So integers between 5 and 20. Right, so you realize that all the entries here obey or fall within that range. And it's a 3 by 4 matrix. Now, in a more crude way, you can create matrices by merging vectors. I consider that a bit crude because it can look cumbersome, but I mean, there are cases where you might actually find this helpful. So with the typical vector creation methods we looked at, the column operator and then the link space, log space, and so on, you can stack some of these essentially to create matrices. And one thing you need to know that in order to obey the rules of matrix entry, you most of these operators will need to have the same number of elements when they are stacked. Right? So each stack or the member of the stack, every member of the stack should put out the same number of elements really to allow you to obey the rules of matrix entries. So let's see a few of those. So you can merge horizontally. You can place vectors side by side to form columns. You can also vertically stack on top of each other. So just like we like to create the matrices, we stack rows on top of each other or we place columns side by side. Now, vectors, if you're merging them horizontally, they need to have the same number of rows. So that's just if you have a column vector, say 1, 2, 3. Let's try to put that somewhere. Now this is a column. So if you want to place another vector to the side, they need to have the same number of rows. This is row 1, row 2, and row 3. Third one. So, 3. So if you want to place another one, they need to have the same number of columns. You cannot place one by it where you just have entries in the first 2 rows and no third one. And likewise, if you're going to place them vertically, if you're going to stack them vertically, in which case, so let's present something like that. Let's reposition this whole thing with some space. So if we're going to stack them vertically, then they need to have the same number of column entries. So this is column 1, column 2, column 3. And if you're going to stack, you need the next entry should also have 1, 2, 3. Just as this is also expected to have 1, 2, 3. So that really is it. Let's practice some of this in MATLAB. Now let's start with the colon operator. So if we recall, the colon operator is the syntax for it is lower bound, spacing, and then the upper bound. So let's create a matrix B, and for the example we had, so if we just take this, right, this was enough to create a vector for us, and this lower bound 3, upper bound 7, spacing of 2, so that starts from 3, the next number should be 5, and the last number should be 7. So this should give us 3 values in that row. Now when we bring the semicolon, we are ready for the next entry for the next row, right, which is 4, 3, and this should be 10. So this gives us our entries for the second row, and then for the third row, we'll just get that quickly. So that's why I said this can be a bit crude. So one thing to note is that all of these column vectors, right, essentially, which we are stacking on top of each other, are going to give us the same number of elements. So this is going to give us 3 elements, 3, and the next is going to be 5 and then 7. 4, the next is going to be 7 and then 10. 5, the next would be 7 and then 9. So that is the only reason why this works. If we alter that in any way, say we make the spacing 1, now we're still going to have 3 numbers from the first 2 rows. However, this third one is going to give us 5, 6, 7, 8, 9, because now the step size is 1. And that should cause problems. Right? Because that last row there is going to have way more elements than any other row in the matrix. And that is not allowed. So if we try to create the matrix we were using earlier, for instance, say C, 1, 2, 3, 4, 5, 6, all the way to 9, we could have done that using the colon operator, but so 1 to 3. And remember, if you don't specify a step size, the default is 1. So 4 to 6, and then 7 to 9. So this gives you a 3x3 matrix. So you could have also gone about this by creating variables for each row. So for instance, you could have gone a equals 3, 2, 7. Then this would have been a vector on its own. And you could do same for, say, B, which is 4, 3, 10. And then you just create your matrix by stacking these. So let's call the matrix J. And that would be A, B, and then C. So this is neat in a way compared to previous, and it kind of shows instances where this can happen. Maybe you already have some vectors you've been working with them, you want to put them together for some complex operations or some matrix operations, you could just do that along the line somewhere. Now, something similar can be done for lane space and log space. So if you recall the syntax for creating a vector using the lane space operator, the function is lower bound, upper bound, and then number of points. So in a way, respecting the rules for element entry in using lane space is easier because you just have to ensure that this is the same for any row or column for which lane space is going to populate elements. So it's the same process. Let's just try one of these. Then, so let's say we created a matrix V. So 5 points. So this is the first row. Next row. Last row. So that should do it. So the key thing here is to ensure you realize that the number of points for each one is 5, 5, 5. That's how you expect it. If you violate that at any point in time, you get an error. So really this should be 5. If I wanted columns instead, I could have just spaced these, but remember that lane space creates row vectors, so this would also is likely to cause a problem. What is interesting? Yeah, it does not create a matrix, it just creates a long vector, right? Because lane space creates a row vector, and then what this does is it places the next row vector side to it on the side, and the next one on the side. So you just have one long continuous vector. So what you could have done here to actually give you columns is to transpose each of these. And yeah, this should now give you this. You could have also transposed directly. So let's enter without. So let's say the original way. Oh, this is not the original. Yeah, this is the original. So this was the original thing. You could transpose it directly, and we should have the same thing as this. So the transpose operator, remember we used for converting column vectors to row vectors and vice versa, also work with matrices. Right? And all it does is just transpose the individual vector elements in there. So that's it for creating. Now let's try to index, slice, and concatenate matrices as we did for our vectors. So after creating a matrix, you can modify elements, locate, replace some of them, and you can build smaller matrices from bigger matrices. You can append elements to already existing matrices and so on to form larger ones. Let's go straight into practicing some of that. Now let's practice indexing and slicing. So recall our vector V, let's just call it so it's clear. And we could extract anything from this vector. So let's say we wanted this. Now to relocate this element, we first check its row index. So this is row 1, row 2, and then row 3. Now 5 is located in the second row. So that is row 2. Now in terms of columns, this is column 1, column 2, column 3, column 4, column 5. It's in the third column. So that is 2, 3. And once we hit that, we are able to extract 5. So you index using the row and column location. Right, so there's only one number in the second column, in the second row, but on the third column. And that's what we are looking for. Now, if you wanted a range of numbers in here, we have to be a bit crafty about it. Now, say we wanted these two numbers. We wanted 6.25 and then 8.25. So we want these two numbers. So what happens is first the row index. Now, the first number is in the second row. The second one is in the third row. So when we go for them, when it comes to the row part of things, we specify that we're extracting from a range from the second row and the third row, right? The range is from row 2 to row 3, and then they are all in the fourth column. So we just go column 4, and that should give us those two numbers. We could do the same if we were looking for elements from a different column. So say we wanted these three, we wanted 5, from 5 to 7. We wanted these three numbers. They are in the second row. So all we have to do there is specify that the second row, but that is from column 3 to column 5. So when we come here, we go 3 to 5, and that should give us those three numbers. Now we can also extract entire columns and rows. So assuming I wanted everything in column 4, right? I could just suppress the rows. So this is called a suppressor, and then specify that I want everything in column 4. So what you can think of this or read this as all row elements. Right? So once you place this in there, you can think of it as saying every row, right? I want every row in column 4. So when you come to column 4, this is row 1, row 2, row 3. Right? So it's just going to extract this column for you. And then you could also do the same for this. So row 3, but I want all column elements. So I come to row 3, but I want every column. And that should extract the entire row for you. Now let's briefly look at concatenation. So earlier we created two matrices, B and then C. Not deleted them, we still have them in there, so I just want to recall. Now we could merge this into creating a larger matrix called N, and I can go in different ways. I could take the whole of C and just place it by B. So I'm going to do that first. I have B, and if I just separate them with the space, that should give me that. So that just places this by this, and if I go size N, it tells me that I have a 3 by 6 matrix. So 3 rows, 1, 2, 3, and then 6 columns or 6 column entries. Now I could have also gone by vertical stacking, so I could stack these on top of each other. So I could have B and C using the semicolon operator, and that would vertically stack them. So check for size of M, and that's now a 6 by 3 matrix. So most of the patterns for concatenating vectors also work with matrices. You just have to be careful with the dimensions of the matrices you are attempting to concatenate. So for this horizontal stacking, for instance, I just need to ensure that the columns have the same size, right? They are the same number of rows in each one. Because if I try to bring this close, so let's take an example. Let's try to modify some of the numbers. So let's say small c, which has this. Now this will be fine if I was stacking vertically, but it's going to return an error if I assume if I try to stack it horizontally with B, and that's because oh, this is B. This is B. And then if we look at our small c, which just has one row, it means if we try to bring that close to B, we're just going to have one row here, and there'll be nothing underneath, and that's not going to work. However, I could have vertically stacked them, and that would have been fine because it fits nicely underneath. It has the same number of column entries, so that works fine. So you just have to be sure of the sizes and the dimensions of whatever you want to add, and make sure you are operating within the rules. Now let's look at a few matrix operations. So after you have a matrix, you might want to perform some of these operations, arithmetic and so on. And just as we did for vectors, we can do carry out similar operations for matrices as well. So we've spoken about the transpose operator already. Now you can add matrices and subtract, which by default are element by element operations. So we could, let's clear this. Now let's pour some of our matrices again. So we could go add them, and that just adds respective entries. So this is element by element. First row, the first entry is added to the first entry, second to second, and then you end up getting this. You could also subtract. And likewise. Now, aside division and subtraction, we could also carry out multiplication. So this is where it gets a bit tricky. Now, when it comes to multiplication, you have to differentiate between matrix multiplication and array or element by element multiplication. So if you have two matrices and you want to multiply them, you just want to multiply the elements, right? Yeah. You have to indicate that you are carrying out an array operation using the array operator, the dot operator we have looked at earlier. And then there's actually matrix multiplication, which is a row by column operation. So let's take a look at both of them. So assuming I want to multiply B by C, let's use the dot operator first. So this is possible, and the rule for this is both matrices need to have the same number of elements, right? So that there's something to multiply at all. So this should work fine because B and C are of the same size. So all that's happening is 3 is multiplying 1, just as the operation worked in addition. 5 times 2 is 10. 7 times 3 is 21. 4 by 4 is 16, and so on. So you get to the last entry. So that is element by element. And if this is how you want the multiplication to be carried out, you need to indicate it as such. Now, if you went directly to carry out matrix multiplication, one thing to note is this for the rules for matrix multiplication, right? So let's just first confirm that we get a different answer. So let's say Z is B times C. So we get a different answer from the array version. Now, what MATLAB is doing here, or what happens in matrix multiplication, is this row is multiplied by entries from the column, and that becomes one entry in a new matrix. So if you take this 3 by 1, you have 3 plus 5 by 4, and then 7 by 7. So you have 3 times 1 first, which is just 3, plus 5 by 4, which is 20, that gives you 23, plus 7 by 7, which is 49, and that should give you 72. which is what we have here in the first entry, and that is repeated for other combinations as well. The first row again takes on the second column. You have 3 by 2, which is 6 plus 5, 5, 25. That should give you 31. And then 7 by 8, which is 56. And then when you add the 2, you get 87. And that goes on to the entire matrix is populated. So that is how matrix multiplication works. And this is how you ensure that that's what is happening. You omit the dot operator. So for multiplication compatible matrices, you have to ensure that the number of rows in one of the matrices you are multiplying with the other matches the number of columns in the other matrix. And the order of the multiplication also matters to ensure that you are getting the computation, the right computation. So we could just check that out. If we swap these, let's see what happens. And answer changes completely because this is a different operation from this. There's a name for this in math. I believe it's the commutative property, which has to do with the order, changing the order of variables in an operation does not change the results. So it's clear that matrix multiplication is not commutative in that sense. Now, in this particular case, it's easy to obey the rules because matrices have identical dimensions in every sense. And they are square matrices. However, if we're dealing with something like a 3 by 1 matrix and so others, we need to be careful about the order. And so you have to multiply it in such a way that the identical dimensions, right? That is the column and the row that matches are aligned in the multiplication. So let's try that. Let's demonstrate that. So what I mean here is assuming you have a 4 by 3 matrix, and then you have, say, a 3 by 2 matrix. If you wanted to multiply this, the multiplication has to happen in such a way that you end up having 4 by 3 by, I'm going to just use the, let me just say the by, 4 by 3 times 3 by 2. And so that's the inner compatible dimensions, which is the 3 here, and then the 1 here, are brought together close by. So once this collapses, you have a 4 by 2 matrix at the end because this collapses, right? The inner ones collapse. However, if you try to go the other way by going 3 by 2, over 3, you lose that direct compatibility. So let's try that in MATLAB first. Let's use rand to generate. So I think we need to place 10 rand. Generate we're looking at 4 by 3 and 3 by 2. So let's go 4 by 3. Let's assign those two variables. L and M. Again, let's just go 5. That was 3 by 2. Sorry. It's 5 times rand. So these are two matrices. We're going to attempt to multiply them. So if we try L by M, let's see what happens. L times M. That works. Now L is a 4 by 3 matrix and M is a 3 by 2 matrix. So L by M aligns this inner. So we end up having a 2 by 4 just as we predicted. 3 collapse. So you have a 4 by 2 instead. So four rows, row 1, row 2, row 3, row 4 instead. Now let's try M by L. And then we ran into a problem, and that is because these do not align. So we 4 and 2, they are not compatible. So the inner dimensions are not compatible. So those are some of the rules for matrix multiplication you want to pay attention to before you attempt to uh, carry them out. Now, let's just note that scalar multiplication is possible. We don't talk about that because we consider it simple, but you could just multiply any matrix by a scalar. That's straightforward, it should work. So they just multiplies everything L by 2. Just to take note of that. Now, division is just like multiplication. You can go array division. So we could do L. We need this is a 4 by 3. Well, let's just do L on L, and that should give us 1. Out. So that works. And remember, division is just inverse multiplication. So the same rules apply. I'll encourage you to try some of that out. Now let's look at matrix division. The right division symbol in MATLAB is for arithmetic division, right? The actual division in there. Now there's left division, which is used when solving a system of linear equations. So it's particularly used for carrying out matrix operations or trying to solve a system of linear equations. We have some of the standard mathematical ways of evaluating those, but the great thing about MATLAB is regardless of the size of the matrix, so far as the right conditions are met, you can obtain answers for crazy systems within seconds. So the left division symbol is one of the easiest ways to go around about it. So if we take this system of equations, for instance, we have x, y, z, w being unknowns or variables. Now, the coefficients can be put into a matrix. The coefficients determine the scale of transformation for all of these variables. You can see that we just have different equations. They are the same or the same type, similar variables. So the coefficients differ. So this is a matrix of all the coefficients arranged, and each equation here, right, is represented by a row. So we can just put all those equations into one, and then we create a vector for the variables and the solution vector. And so what you're essentially looking for here is the values of these variables that when transformed by these coefficients give you this at the same time. So we can enter this problem into MATLAB directly by creating these matrices. So let's try that. I'm going to clear. So let's create our matrix A. If you look at the entries, so that is our matrix, identical, and then our solution vector. So it's a column vector. So let's call it B. That is 8 minus 3. Then 10 and 7. So the solution, we are looking for this, we're essentially looking for the values for this column vector. And so let's say x is simply A. Then instead of right division in normal arithmetic, we go left division or backslash symbol. and that should give us the value for the answer for these variables. So that's how to quickly solve any system with linear equations using the left division operator in MATLAB. So now we recall a few important concepts in matrix algebra, including the determinant and the inverse. Now, this can also be computed in MATLAB directly. They exist as functions, right? So you can find a determinant of or inverse of any matrix you want by simply calling the determinant and inverse functions. So for our recently computed matrix, that A returns the determinant and inv A returns the inverse matrix. So that's that. Now there are also a host of functions for determining different parameters of matrix. You can find the size. We've seen that's the length, number of elements. So this also works for vectors. That should give us the number of elements in the matrix. There are others, the rank, diagonals, transpose, that's eigenvalues and eigenvectors. All of these are functions within MATLAB, and that allows you to obtain information about the matrix very quickly and in a convenient manner. And so it's clear at this point just the mathematical value of MATLAB and how easily it makes computing or performing mathematical computations. So that brings us to the end of this lesson and to the end of our basic math or fundamental math in MATLAB. Next, we are going to look at how to create simple programs using all that we have learned. I've been Martin, your instructor, and I'll see you in the next lesson.